Well, good morning, everybody. I'm really happy to be here with you today. Excited to talk about 5G. You know, it's all about connectivity as we think back over the past couple of weeks and what we've seen with Hurricane Harvey and Hurricane Irma and Katia. There have been people who've been rescued because of connectivity. So it's a great industry to be a part of. And as our thoughts are with those people, I'm happy to share a few thoughts about how we migrate that connectivity for 5G. We at Commscope are all about connectivity from the fiber side to the RF side, so we do the full RF path as well. So I'd really like to start this actually with a little video. Really an exciting time to be a part of the wireless industry. We've just reviewed the goals of 5G, go over those briefly. It's all about the use cases, the enhanced mobile broadband, up to 10 gigabits per second that we're going to be working on. The ultra reliable low latency, latencies of 5 milliseconds, in some cases 1 millisecond being required, as compared to 4G 100 millisecond specification. And then the massive machine-to-machine communication. So today I'm going to focus more on the enhanced mobile broadband application. I'm going to talk about base station antennas as part of that evolution, increased levels of integration, and wireless network densification. So as we just saw, this evolution of the Gs from 1G, 2G on to 5G, with each of those, the demands of the consumer have evolved as well. So 3G was about mobile data, 4G was about mobile broadband, mobile internet, and 5G is about even more mobile broadband data. And as you see, the data rates tied to mobility as well as fixed wireless, it's really kind of breathtaking to think about what it is we're about to do. All of these come back to Shannons Law, right? Shannons Law tells us the capacity of a system is dictated basically by the signal to noise ratio. We call that sin R in the wireless industry. So if you want better throughput, you need better SINR. Very basic. Every electrical engineer has learned these concepts. So as we look at Shannon's Law, we've got the signal to noise ratio. So either we can make the signal higher or the noise lower. And when we talk about noise, there are several different contributions to the noise. It could be thermal noise. So in a rural area, it would be thermal noise that's limiting the range. It could be interference from adjacent channels, either on the same site or other cell sites. It could even be caused by the same site passive intermodulation. So products getting from the cell's transmitter into its own receiver. All of those things are possible. And it turns out that the base station antenna is actually a critical part of establishing a very good SINR across the serving area. If you think about it, the antenna produces the pattern, right? The radiation pattern. That dictates the coverage. So you want coverage where the signal's desired, and you want no coverage where the signal's not desired. That's how we get good SINR. So the base station antenna is fundamental to good SINR, to good data throughput. That's why we're talking about it. So here's the evolution of the antenna over the past 15 or 20 years. When we were talking about 2G, basically in 1G we had a bunch of omni sticks. We started doing 3-sector with some panel antennas. In the 2G world, in the 2000 time frame, a lot of these were 90-degree antennas in the rural areas, some 65-degree in the more urban areas. And basically what I'm showing here is a low-band antenna, 12 inches wide, 2 ports, okay? And then a few years later, 2003, 2004, we started deploying 3G, which is wideband CDMA, the CDMA technology. And because of certain constraints, we wanted to have more ports in the same width of the antenna. So those constraints relate to the tower loading. Okay, if you have a wider antenna on the tower, it catches more of the wind, and we call that wind loading. And so both tower loading, the actual weight of the antenna, and wind loading, the effect of the wind on the antenna and the tower. And actually the wind loading is the more severe of those two in most cases. So in order to reduce wind loading, we put 4 ports in the same size that we had previously put 2 ports. So what I'm showing here has a low band and a high band column array in it. And it was serving 2G in the low band, 3G in the high band in this case. Well, along came LTE in the late 2000s, 2009, for all the same reasons, right? Wind loading, tower loading, actually lease rates for the operators. We want to be able to put more ports in the same size. So in those same 12-inch widths, we put six ports. So there's a lot of innovation that went into doing that. A lot of work to keep the low band and the high band from coupling together and interfering with the pattern of the other band. That's where a lot of the magic sauce was, secret sauce was. And typically we talked about antennas here in North America as being either 4 foot, 6 foot, or 8 foot in length, depending on the gain that was needed in the application. In CDMA, we saw a lot of the, with the 3G, we saw a lot of those 90-degree antennas being replaced with 65-degree. The CDMA just could not work well with a 90-degree antenna because of the overlap, which robs both capacity and coverage from a CDMA signal. With LTE, what we saw is where previously 4 foot and 6 foot antennas had been deployed, we saw now 6 foot and 8 foot antennas being deployed. So not only are we restricting the azimuth beam width, but we're also restricting the vertical beam width. And when we talk about 65 degrees, of course, we're talking about the half power beam width and the azimuth plane. Just make sure we're all level set there. And then as we moved into 2014, we saw the transition of LTE into additional bands. So we had the 700 megahertz band. So here in this antenna that I'm actually showing, there's a single low band array, but we're providing service for 2G in the 800 band and 4G in the 200 band. And we do that by building in diplexers, so basically crossband couplers to do low loss splitting from the input to share the array. And then the transition more recently, we saw in the industry, we saw it evolve from two transmit, two receive for LTE to two transmit, four receive. We saw that about the same time as voice over LTE was being deployed. That helps the uplink range. And now really the transition is to four transmit, four receive. So that's to support 4x4 MIMO in the FDD bands. And so this final stage that I'm showing here is transitioning to 4T, 4R in the high bands and two low bands. So currently today it'll be primarily 8 and 12 port antennas that are being deployed. So this is one of the mega trends, is the integration of the antenna itself, more passive capability being built into the antenna. So what I'd like to show here is just the map as we look to the future. How is the antenna going to evolve? And in order to do that, in order to really understand what's going on, we have to split and divide, talk about 6 gigahertz and below, and talk about above 6 gigahertz, because they're very different and we need to treat them differently. And then going up this other axis, we've got the 4x4, 2x2, 4x4 FDD MIMO on the lower left. We've got TDD, beamforming MIMO, and then we have full dimension or massive MIMO at the top. So here's how we split it up to explain these different concepts. So lower left here, we've got, this is the bulk of antennas that have been shipped up till now. These are FDD, multi-technology, multi-frequency, multi-band FDD antennas. That's what the previous slide was talking about. And then as we look to the future, we're seeing more and more TDD, so time division duplex bands being deployed. If I go back 2 or 3 years, I see that there are about 1 in 8 LTE networks has TDD. Today it's 1 in 5. And if I look to the future in 5G, the vast majority of the bandwidth will be time division duplex. So we're moving to a TDD world in wireless. What we see in this TDD world is multi-band TDD. I'm actually showing an antenna here we've shipped a few thousand of. The big X's are the low band cross-pole elements, dipole elements. These 2 rows of elements are FDD high band. And then where you see the 4 rows of elements, that's TDD. And so it's a combination TDD FDD antenna that's pretty popular. If I go straight up, now I'm into the full dimension MIMO or massive MIMO. And what we're talking about here is sub 6 gigahertz massive MIMO. So when we say massive MIMO, it's generally meant to be 64 elements or more. So 8 by 8 arrays is generally considered massive MIMO on the base station side. So we see some limited products in this range. And what we're trying to do below 6 gigahertz with massive MIMO is take advantage of multipath. So for example, in the simple case, 2x2 MIMO, if you have multiple paths for the signal to get to the user, to the UE, then split the data stream in half and send half over each path. You've doubled your capacity. With 4 paths, then you've quadrupled your capacity. So that's the basic concept, spatial multiplexing. So below 6 gigahertz, when we say massive MIMO, we're talking about spatial multiplexing, and we're talking about multi-user MIMO. So if you're in an area where there's a lot of really strong, good, rich multipath, then you can have multiple users using the same resource block, same frequency at the same time, and have spatial separation between those users. So that allows even more capacity improvement for the cell, not on a per user basis, but on a per cell basis. So below 6 gigahertz, when we say massive MIMO, we mean 6 or 8 streams of data that are split across multiple users using multipath. All right, now let's go up to 28 gigahertz. We call it millimeter wave. It's actually centimeter wave. But we go up to above 6 gigahertz. When we talk massive MIMO, it's completely different. We still have 8 by 8, let's say 64 or 128 elements, but now we're doing coherent beamforming. We don't want multipath at 28 gigahertz because of the path losses involved. So what we're trying to do here is have line of sight maximum gain. So we're focusing that beam on the UE or on the CPE, the customer premise equipment, to get the maximum link budget we can. So above 6 gigahertz, massive MIMO means coherent beamforming. You might have 2 streams going to a user or 4 streams going to a user, but it's not the multipath that we talk about below 6 gigahertz. Okay, so let's talk about increased levels of integration. We talked about integration within the antenna, but there's another level of integration where we are integrating parts of the transceiver into the antenna as well. And there are different levels of integration. For example, on the left, we've got basically one remote radio unit bolted to an antenna. We call that an integrated antenna. And the benefit of this is that you don't have the jumper cables between the radio unit and the antenna. We're going to see maybe a half a dB of improvement in the loss budget as a result. As we move to the right, we have more and more transceivers integrated into the antenna function. So in fact, what we're seeing today on the right is we may have 8 vertical elements and we may have 8 columns. All right, so you have both azimuth and vertical beam steering. And there are some benefits. Because of the narrow beam, you're able to improve that signal to noise that we're talking about, that SINR, and improve the throughput. The other thing that happens with these fully active antennas is that we see there are more and more transceivers. Every transceiver has a duplexer. That's great for the duplexer suppliers, right? Every element has a duplexer. Every element has a transmitter and a receiver. Every element has a front haul link back to the CU. So what that means is you have more flexibility, you have more capability. At the same time, it's going to impact reliability. Every one of those transceivers has a failure rate. Every one of those duplexers has to be connected. So all of those interconnections, all of those active components can result in failures. And so I think time will tell just how popular this approach will be. Probably in the next 5 years, it'll be in the 5%, maybe 10% range, applied specifically to hotspots where there's high traffic demand. There's also another factor I mentioned earlier with wind loading. Typically on a sector, on one face of a sector, the operators are deploying 3 or 4 antennas. On a typical, some cases it's only 1 or 2. If you've got one of these units that's single band and it's tying up one of those spots, and you've got an operator with 6 or 7 bands, then that gets kind of restrictive on what they can do. So I think for these to be super successful, they're going to need to be multi-band and highly reliable. So time will tell if those challenges can be met. The other thing, though, that we did see in today's world is a lot of the antennas being deployed are narrower beam widths. With 3G, we went to 65 degrees. With 4G in some of the urban areas, we're starting to see 3-sector site with 45-degree azimuth half-power beam widths. And that's to help, really reduce interference. They don't work so well in the rural areas, the 45-degree, because you get a coverage gap in between the sectors. But in a highly dense market, that tends to fill in with the multipath and work just fine. Okay, another form of beamforming is what we call a multi-beam antenna. So here we have 2 beams per sector, 5 beams, 9 beams per sector. Each of those are being deployed today. And again, here the benefit of this approach is that you have higher gain, so you increase the signal power for C over I, for signal to interference, and you decrease the noise because you're containing the signal just where you want it to be. We see some movement towards 6-sector. Here in North America, it's probably 1% or less of sites will have 6-sector. In some parts of the world, there's one network in Thailand where over 3/4 of the sites are 6 sector or above. And they have excellent throughput, they have really good performance. So it's really going to come down to, and a lot of those are on rooftops, and so it really is going to come down to the morphology, where's the demand needed. We also see the 5-beam and the 9-beam antennas. They're very popular for venues like a stadium or a temporary capacity situation like an outdoor concert where you need to bring in a lot of capacity. And this approach helps not only because of the improvement to SINR, but also because you're deploying, every one of those beams has its own BTS, right? Has its own eNode B. So in the area where you had one eNode B or one base station worth of data throughput, now you've got 5, or you've got 2, or you've got 9, depending on the application. So when we talk about data density, gigabits per second per square kilometer, for example, how much data can I pump into a given area? This is going to help you dramatically increase the data density in a given area. Another way to densify the network, which is a key trend as we move to 5G, is in the deployment of small cells. So as we look back 3 or 4 years, there was a lot of buzz about small cells. We talked about just a grid of small cells going to cover the entire or the key parts of the network, and that didn't happen. Why didn't it happen? Well, I think a big part of that is the cost and the time to deploy those small cells. There are things happening today. There's legislation in process in many of our states to speed up the deployment of small cells on poles and mini towers or micro towers. And also there's a lot of work being done to reduce the cost of deployment. So what we have seen are kind of the laser focused deployment of small cells. So where is the data demand the highest? And the payback is going to justify the deployment of that site even with today's costs. And those costs are coming down. If we look back over the last 18 to 24 months, there are over 30,000 small cells deployed in North America. Other parts of the world, even larger numbers have been deployed. India has deployed over 50,000. And so another driver for small cells, another factor that will help move them forward and is helping move them forward, is the preparation for 5G. So the difficult part, or probably the most difficult part of a small cell, is getting it in place. So we talk about PBS. I'm not talking public broadcasting. It's power, backhaul, and site AC. Okay, so with PBS, you've got to get power to every pole that you put a small cell on. You've got to get backhaul, and typically that means fiber. It could be microwave, and you've got to acquire the site. You got to get the permissions to be on that site. That alone can take months or years to do. So PBS. So a lot of what's happening today that is helping move small cells forward is the preparation for 5G. And what I'm hearing is, hey, this is a 5G network. We're just using it for 4G in the meantime until the 5G electronics come along. And oh, by the way, when they do, the hard part is done. We'll just swap the electronics and turn it to 5G, or add the electronics and turn that site to 5G when those electronics are available. So that's another key driver. I think we're sort of on the cusp where we'll start to see more and more small cells deployed as we prepare for 5G. So let's talk a little bit more about MIMO. I mentioned it briefly before. MIMO is a terminology that we use that really covers a broad range of technologies. I talked about spatial multiplexing, where we take a bit stream, we split it, and in a high multipath environment, we basically send different streams over different paths to double or quadruple or increase the input. What we're seeing right now worldwide is everybody's basically that has LTE is doing 2x2 MIMO, and a lot of people are moving to 4x4 MIMO. To my knowledge, there's one handset. I'm sure there'll be more soon that can be on the other end of that. So you've got to have 4x4 MIMO. You have to have 4 antennas at the base, and you have to have 4 antennas at the mobile. And those are limited now, but they'll increase. And as they do, the percentage of 4x4 MIMO traffic will increase also. There's another thing called transmit diversity. So this is where you have 2 transmit antennas. They're both transmitting the same signal coherently. What that does is extend the range of the downlink. And then beamforming. Beamforming is actually an aspect of MIMO. For TDD, we have coherent beamforming. For FDD, we still have beamforming as part of MIMO, but it's less precise. With TDD, the transmit and the receive are on the same frequency. So you know exactly how to set the transmit coefficients to get precise coherent beamforming. With FDD, they're on different frequencies, so you have to estimate what that beam is going to look like based on what you learned from the receive channel. And we have what's called a code book, and in that code book there are different indices, and the algorithm will just pick the best index to generally find a beam that matches for FDD. And we've talked about antenna, active antenna system, and massive MIMO. This is where we're getting to 64 or greater elements, and we'll go into a little more detail on that. Again, as we talk about beamforming, beamforming is just not beamforming. You got to know what it is you're talking about. So there's cell-specific or cell-wide beamforming, and there's user-specific beamforming. Cell-wide beamforming, so when I showed those multi-beam antennas, those are cell-wide. Everybody in the coverage area is going to have the same coverage, right? And so the same weights for all users and control channels. This can be done digitally or by RF, as with the multi-beam antennas. And it can be dynamically reconfigurable or it can be static. We see both. But the point is, it's the entire cell. Everybody in the cell has the same coverage. And then there's user-specific beamforming. So in this case, what we're talking about is it's done digitally. It has to be done at the baseband, and it's per user. So every user has their own beam. If it's TDD, it can be a very nice coherent pencil beam, and it's directed at, so every user simultaneously has a different beam in this case. And that's a really powerful approach to reducing interference and to maximizing the user experience for that user. So in our previous examples, the millimeter wave, that's a per user. And the massive MIMO could be per user as well. So one more look at this. Sub 6 gigahertz. Again, to talk a little more about the antenna, this is a planar array. We could have a digital transceiver on every element or group of elements. And I think the economics will drive that. You may see 2 or 3 elements per transceiver, or 4, depending on how the architecture is. It's going to be multi-user MIMO. Multi-user MIMO typically helps the capacity of a sector, maybe not of an individual user. You use those same resource blocks going to multiple users. That means you have more capacity in that sector. And each element also has its own front haul link, its own CPRI link, if you will. And the UEs have send a lot of information back to the base to help with the forming of that beam. And then a reminder here on the RF beam forming for the millimeter wave. Again, this is still massive MIMO. It's TDD though, it's coherent beam forming. We don't care about, in fact, we don't want multipath. We want point to point. We want line of sight, maximize the link budget, maximize the gain, get as much signal as we can to the user to maximize the throughput. It's what we called years ago the smart antenna approach architecture. Basically, the way this would be implemented is a phase shifter, RF phase shifter, and some amplitude control on each element. All right, so you have an amplifier to overcome the loss of the phase shifter. You're going to phase shift each element to get the beam that you want, and then manage that across the different columns. And then 1 beam per digital chain. So what you might see with 128 elements, you might see 16 transceiver chains, for example, as a typical architecture. So what I've talked about, base station antennas are evolving and have evolved to support the needs of the Gs as we've evolved from 1G to 2G and on here 4G moving to 5G. And dramatically different compared to what we had 10 years ago. They hardly look like the same unit. Network densification, I think we're on the verge, the very beginning of network densification from the perspective of deploying small cells and deploying higher orders of sectorization. But that will pave the way for 5G, and that preparation is beginning today. And then we continue to see integration of more capability into the base station antenna to help keep costs down and to help leverage these bandwidths, these new frequency bands that we've gotten. And these are the three key takeaways for the evolution to 5G for base station antennas. Thank you very much.